Okay, so my name is Javiera Guedes, and I'm going to talk about Eris and some of the latest work that we've been doing in the simulation. This work is done in collaboration with Simone Caligari, Annalisa Pilepich, Michael Cullen, Xijing Shen, Piero, Lucio, and the usual crowd. And of course, the entire gasoline community is involved in this kind of simulations. Is there a laser pointer? No. Laser. Okay, I had this.
So it's just this button there, and that's the green laser.
Okay. And so a lot of the stuff I'm going to be talking about today, just describing basically the simulations. And this work is in this paper, Guedes 2011, and then the newer stuff, I'm gonna touch on all these papers, but I'm gonna let the individual people do it. And I'm gonna talk about this paper that may come out in 100 years at this rate. So the date is not a typo there. So the philosophy for the simulation was to try to do one simulation at very high resolution to try to understand the process of how this one spiral galaxy forms instead of having a large volume with many, many galaxies that are not properly resolved. And so the idea was to follow the recipe for the formation of a galaxy as in Governato et al. 2010, in which they form a dwarf galaxy with a resolution of about 80 parsecs. And they show that, that they get a very exponential profile as opposed to the results of previous simulations. That was a big advancement in the field. Let's see how this works. So what do we mean by realistic galaxies here? So basically, so this is their simulation. This is the Milky Way. And we go way beyond just trying to visually seeing whether the galaxy is a good match to the Milky Way. So Fabio Governato in the HiPACC summer school last time, he said, be skeptical of your simulation until you prove yourself wrong, or something like this. He didn't exactly say this. He denies it, but this is basically the point I got. And really, I mean, you have to test many, many things in order to say that your simulation reproduces a spiral galaxy. This includes the Tully-Fisher relation, the rotation curve, the star formation history, Koenig-Schmidt fluoration at some level, the M-star M-halo relation, cold gas fraction, Bulge-to-Disk ratio, and you name it, including also outflows and things like that. So it's a thorough study of the simulation. And what can we learn from this? Well, we can understand how the major components of the galaxy formed. Although we have no statistics, we only have one galaxy basically. So how the balls, the bar, the disk, the stellar halo, how those evolve. And we can also make predictions. That Xijing Shen is going to talk a little bit more about this. But for example, can we observe cold flows and this dark matter annihilation signal offset that Michael Cullen talked about yesterday. Also, we can look at the evolution, the distribution of stellar populations, stellar migration, and this in detail. So the simulation is a product of gasoline. It follows the formation of a light Milky Way galaxy of 8 × 10⁻11 solar masses. And it was selected to have a very quiet merger history. So there's no mergers, basically, after redshift 3. There's only very minor mergers, ratios less than 1 to 10. And the spectral resolution is 120 parsecs. We follow that with 18.6 million particles within the virial radius. And as you look at the movie, you can see already that there are some problems with the simulation. There's this clumpy instabilities that cause a lot of problems and that people are talking about. And now we're able to fix this kind of things. So Eris is kind of an intermediate step between just getting galaxies really wrong and getting galaxies really right, which is what we're trying to do in this comparison project. Also, Eris includes low temperature metal cooling. Heating by UV background, supernova, star formation, and so forth. There's no explicit wind prescriptions. And the star formation density threshold is extremely high because we have this high resolution. So we set that to 5 atoms per cubic centimeter, which is a factor of 50 over what previous simulations had done at the time. But it was a very expensive simulation. We spent 9 months running the simulation. So it's not the kind of thing that you can do for many galaxies as a statistical sample. You have to just really go one by one. And there's a lot of stuff missing here that people have developed recently. High temperature metal cooling by Zijing Chen, for example, she's going to talk a little bit about new simulations that include this. H2 star formation, Charlotte talked about it. Metal diffusion, stellar radiation, early stellar feedback, as is the Stinson et al. Papers. And yes, some of these ingredients are included in the new simulations. So what are the properties of the galaxy at redshift 0? So Eris is 0.79 times 10 to the 12 solar masses. The Milky Way, yeah, I don't know. I don't know what number to really give you for the Milky Way anymore. But, you know, this is a light Milky Way. Something I want to stress is that the baryon fraction in Eris is 30% lower than the universal value. Actually, we don't know what the value for the Milky Way is because we don't know what these baryons are. So we can only count basically stars in cold gas. But it's definitely lower than the universal value, which is a good sign because there's outflows. And the Bulge-to-Disk ratio is comparable to that of the Milky Way. The scale length is also comparable. And the star formation rate today is 1.1 solar masses per year. At the time when we ran Eris, this was the picture. So basically, there were simulations by Scannapieco et al., Brooks et al., that had 1 and 2 million particles within the virial radius. We went up to 18 million particles within the virial radius distributed in gas, dark, and star particles. And then the softening, also we reduced to 120 parsecs, which is a big improvement from previous simulations, and so forth. And the other parameter that we raised quite high was the threshold for star formation. And the threshold for star formation is really important because this is radius versus number density. If you make a plot of Eris and Eris, a twin simulation of Eris, which has a lower threshold for star formation. So this is the density, the number density of particles in both simulations. And if you put the threshold here, what you get is really inhomogeneous star formation. So the stars only form at this very high density peaks. Whereas if you put the threshold really low, this is at the same resolution, then you get star formation happening everywhere. And you get a lot of warm gas, you know, everywhere. So feedback is really not being efficient in this case. Feedback is very efficient in this case, and it's able to blow out outflows. And this is the difference. If you have, this is an example of redshift 1. The disk in the low threshold simulation is much smaller than in the high threshold simulation. You see it's 50% larger than Eris, 30% less massive. It has 30% higher gas fraction and so forth. So the big difference in going from low to high threshold. And so let's compare it to observations. And as I said, we do several tests. The first one, of course, is the Tully-Fisher relationship. This is the V80. Is the velocity at the radius at which you have enclosed 80% of the light. And this is the IBAM magnitude, and this point is calculated using sunrise for the simulation. We can also compare the rotation curve to that of the blue horizontal branch stars, and it does pretty well. We don't really know what's going on at the very center, but it's possible that this peak is a little bit too high. So if you take this is the gas density, the gas surface density, and this is the star formation rate surface density, and you put this together and try to see whether we match the Kenica-Schmidt relation, for example, then what happens is that, so this is the BGL plot that you know very well. So H1 doesn't really correlate with star formation because stars don't really form out of H1, although, you know, at very high redshift, maybe this is not the case. But star formation rate does correlate with H2. And in the galaxy, in the simulation, we don't have H2 at this point. But, you know, in the regions where we have H1 peaks, if we compare that to the star formation rate, we're doing pretty well according to a set of nearby spirals. So we cannot really reach these high densities, but we can reach the densities of a few nearby spirals. This is an image of Eris in the I-band, and what we can do with this image is to, first of all, do a surface brightness profile and fit using observational codes like, what is it called? I can remember. Sunset? No. Anyway, so we can fit for the bulge and the disk, and I just forgot the name of this code. But anyway, sorry, GalFit, and then GalFit, yes. So then you can get bulge to disk ratio in the way the observers do it, and we get a Zuirch index of 1.4 and a scale radius of 2.5, which is pretty good, in comparison to nearby spirals. Again, this is the stellar mass of nearby spirals. This is the Zuirch index of the bulge. We're doing pretty well in this. Also, the bulge to total ratio is a little bit on the high side, but still within what we see in the local universe. Also, there's little details in galaxies. For example, the surface brightness breaks that occur at a characteristic radius in nearby spirals. In this case, 12 kiloparsecs in Eris, that happens at 10 to the 7 kiloparsecs. But if we put this in context with other galaxies, then we see that the break radius is in well agreement with the other spiral galaxies, and the extrapolated inner surface brightness is also in agreement with nearby spirals. So even these little details in the disk are in agreement with observations. There's other things that we can study in the simulation that are using the particles. For example, we can study the angular momentum distribution. And this is an example of a set of Scanapieco's galaxies where they have, so in this plot, 0 represents the location of the bulge. So all the particles that are around 0 are bulge particles. And the particles are around 1 are disk particles. Not only bulge particles, but also generally spheroid particles. So they can be also halo particles. But in Eris, this is what we get. So we get a very small spheroid and we get a large disk. So that was an improvement. We can go forward with this and look at the star formation history of the different components, and we see that the spheroid begins to form really early, and today it's really not forming any more stars, whereas the disk starts forming a little bit later, and today it's forming stars at one solar masses per year roughly, with a peak at the time when minor mergers occur. There's other features of the galaxy, like the holiness in the H1 distribution, for example, and this is well represented by the simulation. This is a movie of a very high time resolution of the simulation. So this is the time resolution here is 1 million years, and you can see these bubbles forming and so forth. This is a movie that we used for the project that was described yesterday by Mike Cooley. The other problem that simulation had before is that we really had to extend this axis here to put the values for previous simulations. And Eris is here, so it's matching the M star M halo relation. But later, also newer simulations are also starting to match this relation at low redshift. At high redshifts, however, Eris is not doing very well at all. So this is at redshift 0, redshift 0.5, 1, and so forth. And we are up here with the other simulations. So I call this the forming too many stars at high redshift catastrophe. So I don't know if it's a new catastrophe. I don't know if this is something that we need to address. I don't know if we believe abundance matching at redshift 4. We probably do. Do we want to address it as well in the new simulations? So as I said, new simulations that have early stellar feedback, for example, are doing pretty well in matching the M star M halo relation at redshift 0, but also throughout cosmic time. And this is an example of one of those simulations by Stinson et al. So maybe this early stellar feedback can help alleviate this problem, solve the catastrophe. Other things that we checked is the hot gas in the simulation. One way in which we can do this is calculate the dispersion measure of the hot gas, so by counting electrons from the Milky Way to the location of the LMC, for example. And we find that dispersion measure value is pretty close to what is found in the Milky Way. So it's not just that the structural parameters of the galaxy are right, also the hot gas content seems to be right. And Xijing Shen is going to talk about the outflows and how that matches observation, and I'm going to leave this data. But also, what can we learn from the simulation? So basically, I want just to focus on the pseudo-bulge. And the pseudobulge is basically characterized by having a low Zuirch index, as I showed. And it's a little bit disky. You can see this in this image. This is an image of a real spiral. This is Eris here. So this is a plot of stellar mass versus the fraction of galaxies that have a certain kind of bulge for that stellar mass. And you see that classical bulges really dominate at high stellar masses, and pseudobulges dominate at lower stellar masses. At the mass of Eris, this is kind of half and half. And the galaxies that have a bulge-to-total ratio of 0 really dominate at slightly lower masses. So Eris definitely has a pseudobulge. And we want to see how that forms. In terms of colors, Eris is in the blue side of this diagram. This is bulge-to-total ratio versus U minus R color. So we can calculate these colors using sunrise again. And we can place our galaxy in this diagram. And it's definitely here with the pseudobulges as opposed to being up here with the classical bulges. Same in terms of Zuirch index and inner surface brightness. So it's out here with the pseudobulges. And so in order to try to understand how the pseudobulge forms, we have to sort of define what the pseudobulge is in terms of particles. And the way we do this is very simple. So we take basically, according to the surface density profile, we take everything within 2 kiloparsecs, which is at the point where the bulge or the pseudobulge begins to dominate the profile. And we remove everything that is kinematically cold, everything that is basically part of the disk. And so if you in an angular momentum plot, this is the old plot that I showed you before, so the distribution of angular momentum, this is the spheroid and this is the disk. And if you plot everything within 2 kiloparsecs, then you get this solid line. If you plot everything within 2 kiloparsecs that is very hot, then you get this yellow line. And we can try to work with the particles and see how they formed. If you plot the profiles of these particles in terms of density, then you get these nice profiles. So I trace these particles back, and basically what you get is that the pseudobulge forms very early on. It forms an early burst of star formation at redshift between 3 and 5. And there's a little bit of star formation at the time of a merger at redshift 1 or so. And then there's no star formation afterwards. This is what's going on in Eris. I don't know if reality really works this way, but definitely for this pseudobulge, it's a really old pseudobulge. And this is a thin disk, so this is all the particles in that peak. And you can see that they start forming a little bit later, but then they continue to form stars until today. And you can see that you can compare where the stars formed to where they are now. And the stars that are in the pseudobulge today formed, really locally within 4 kiloparsecs, and today are within 2 kiloparsecs. Whereas in the disk, there's a little bit of migration. Stars that formed really close in today are spread out through the volume, through the disk. And in terms of merger history for the pseudobulge in the thin disk, really they have a very similar merger history, meaning that the path through which the pseudobulge form and the disk form are not very different. It's not like the pseudobulge form via mergers, for example, exclusively. It's a process that goes on together. And the pseudobulge evolves over time. And so the very first thing that forms at redshift 4, so this is the sunrise composite images of the galaxy face on and edge on. And then on the side, I'm plotting the inner 5 kiloparsecs, just a contour plot of the stars. And the very first thing that forms is this pseudobulge stars, but it forms with a very strong bar mode. And you can see this from I'm plotting here the Fourier M2 mode of the bar as a function of redshift. So it forms with a very strong M equals 2 mode. Then at redshift 3, there's a very active minor merger attack to Eris. So basically, these minor mergers destroy this bar at this redshift 3. And then the bar reforms very quickly by redshift 2. And then afterwards, it continues to decrease very slowly. By redshift 0, we have only a nuclear bar. So you can see this, what happens. This is the same plot as I showed before, but now you can also see what happens to the velocity dispersion in the inner regions. And so very high redshift, as you have more and more mergers, the velocity dispersion increases. And then after the one merger, there's one more kick, but then afterwards it stays constant through redshift 0. There's a lot of variation in the fraction of gas that is in the inner regions, but in total, the amount of gas that is accreted into the inner 2 kiloparsecs, for example, only increases by a factor of 2, including because of star formation outflows and recycled gas. And if you want to know where the gas that is today at within 2 kiloparsecs, where that gas was at redshift 1, then it's impressive because this is a scale of 2 kiloparsecs here. This gas at redshift 1 was out at 200 kiloparsecs or more. So it's really a cosmic bathtub of sorts. There's also redistribution of angular momentum during mergers. This is before the merger, you had more particles here sitting in the disk. After the merger, particles move into these hotter regions because particles are heat up during these mergers. So part of the pseudo-bulge particles also come from the disk via this merger heating. And the bulge-to-disk ratio varies over time in a way that is not monotonic, so because the bulge is constantly changing. But the bulge and the disk actually do grow together. They're not separate processes. And if I just show what happens to the pseudo-bulge particles over time, they form a strong bar. The bar is destroyed. By redshift 2, the bar is reformed again. And as time goes on, you get a merger there, and then the m equals 2 mode basically is destroyed. Then you get this nice pseudo-bulge in the end. I can talk about stellar migration if you're interested later. Stellar migration has an effect on the gradients in metallicity in the disk, but I'm just going to put up my summary because apparently I ran out of time.
Thanks.